a situation where maybe an access point has a fixed output. Access point's output's 100 milliwatts. The only antenna that we can find is an omnidirectional antenna with a plus 20 dBi gain. If we put this equipment together, we would violate all of the FCC rules for power output. So an attenuator could actually be added to decrease the RF signal down to 30 milliwatts before it actually entered the antenna. This configuration may allow us to fit within the power output guidelines that the FCC identifies. Now, there are going to be some common options with attenuators that you need to be aware of. First of all, they're available as either a fixed loss or a variable loss type. Like a variable amplifier, variable attenuators allow the administrator to configure the amount of loss that's going to be caused in the overall RF signal, and do so precisely. Variable RF attenuators are not used in wireless LAN systems due to the FCC regulation on certification. They're typically used more in site surveys in order to determine antenna gain, necessity of amplifiers, and so forth. When choosing what kind of attenuator is required, you want to consider similar items that you would have used to consider an RF amplifier. The type of attenuator, whether it's fixed or variable, the impedance, the ratings for input power, loss, and frequency response, as well as the connector types need to match for all of the components on the wireless system. All attenuators should come with a calibration report and a certificate. It may not be feasible to disassemble your wireless LAN in order to calibrate the attenuator annually. So make sure, as per FCC guidelines, that the attenuator meets the manufacturer specifications prior to installation. Configuration of attenuators is not required unless a variable attenuator is being used. Once again, mostly in a site survey. Realize that you will not likely see the FCC certify a system that has a variable attenuator, one of the reasons why they're not as common as a fixed device inside of a wireless network. Another major component in wireless LAN design is understanding a lightning arrestor. A lightning arrestor is used to shunt into the ground transient current that is caused by lightning. Lightning arrestors are used for protecting all of your hardware, such as your access points and your bridges and even your antennas, as well as your coaxial transmission lines. Coaxial transmission lines are most susceptible to surges from nearby lightning strikes, but there is one common misconception about what a lightning arrestor is going to do. They are not designed to protect you against a direct lightning strike. In fact, if a bolt of lightning were to strike your antenna and hit your wireless LAN, even with the best lightning arrestor on the market, your antenna is going to be fried and your wireless LAN is probably going to be damaged through and through. A lightning arrestor is not meant to withstand a direct lightning strike, nor is it designed to protect your network from such a strike or such a fault that may exist. Lightning arrestors are generally designed to shunt or redirect a surge of electricity up to 5,000 amps at up to about 50 volts. Depending upon the type, what they will do is, first, when lightning strikes a nearby object, the transient currents are introduced into the antenna or the RF transmission line. The lightning arrestor will sense these currents and immediately ionize the gases that are held internally to cause a short. This is called a path of almost no resistance. This will go directly to earth ground. Anytime objects are struck by lightning, an electric field is built around that object for just an instant. When the lightning ceases to induce electricity into the object, the field collapses. And when that field collapses, it induces high amounts of current into nearby objects, which in this case would be your wireless LAN antenna or a coaxial transmission line. Lightning would be discharged as direct current pulse, but then causes an alternating current component to be formed, resonating as high as 1 gigahertz. However, most of the power is dissipated from DC to 10 megahertz, and that's what a lightning arrestor is designed to do, is to protect you from a nearby strike. There are going to be some options with the lightning arrestor itself. First and foremost, it's going to cost probably around $50 to $150 for any brand. However, there are some attributes that should always be considered when you purchase it. First and foremost, it should meet the IEEE standard of less than 8 microseconds. Most lightning arrestors are able to trigger a short to earth ground in under 2 microseconds, but the IEEE has specified that it should happen in no more than 8 microseconds. It is very important that it's at least this number and that you meet this standard at minimum. In addition, we might want to identify whether or not the device is going to be reusable. Some lightning arrestors are reusable after a lightning strike and some are not, kind of like a surge protector. It's more cost-effective to own an arrestor that can actually be used a number of times before it's completely fried. Some reusable models will actually have a replaceable gas discharge tube element, and they're cheaper to replace the tube than to replace the entire arrestor. Other models may have physical characteristics that allow the lightning arrestor to do its job properly multiple times without having to have any replaceable parts at all. You also have to consider the voltage breakdown for the gas tube. Some lightning arrestors do support the passing of DC voltage for use in powering RF amplifiers, and others do not. A lightning arrestor should be able to pass the DC voltage used in powering RF amplifiers if you plan on placing an RF amplifier closer to the antenna than to the lightning arrestor. The gas tube breakdown voltage should always be higher than the voltage that's required to operate inline radio frequency amplifiers, kind of like a fuse. It's suggested that you place the lightning arrestor as the last component on the RF transmission line before the antenna, so that the lightning arrestor can protect all of your amplifiers, all of your attenuators along the line between the antenna and your bridge or access point. You also have to consider the connector types. Make sure they're the same as the rest of the devices in your radio frequency circuit. And frequency response identifies the specification of the lightning arrestor itself, and it should be at least the same highest frequency that's used in your wireless LAN. A good example of this is that if you're using only a 2.4 gigahertz LAN, a lightning arrestor that is specified for use at up to 3 gigahertz is always best. Match your impedances also, just like with every other device. Normally impedance is 50 ohms in most of the wireless LAN devices that we deal with. We also have to worry about insertion loss. The insertion loss, it can be significantly low, perhaps 0.1 decibels in most cases. So usually it won't cause too much of a radio frequency signal amplitude loss. However, you want to be aware of that. Anytime you insert a new device into a radio frequency circuit, you will have a certain amount of insertion loss. You also want to double check on your VSWR rating, that ratio. The VSWR rating of a good quality lightning arrestor is around 1.1 to 1, but some may be as high as 1.5 to 1. The lower ratio of the device, the better the device is going to be, since the reflected voltage degrades the main radio frequency signal. And last but not least on the lightning arrestors is the warranty. Regardless of the quality, the unit can malfunction. You want to seek out the manufacturer that is reputable and does offer a good warranty on the lightning arrestor. Some manufacturers offer a highly desirable, no matter what type of warranty, and those are really the best ones to have with this type of device. Another object that we have that may exceed the time of this section, another object that we have is called a radio frequency splitter. Now, a splitter is a device that has a single input connector and multiple output connectors. An RF splitter is used for the purpose of splitting a single signal into multiple independent radio frequency signals. Use of splitters in everyday implementations of wireless LANs is not recommended. You got to remember that. But sometimes two 120-degree panel antennas or two 90-degree panel antennas can be combined with a splitter and equal length cables when the antennas themselves are pointing in opposite directions. This configuration will produce a bidirectional coverage area, which may be ideal for covering an area along a river or a major highway in certain situations. Back-to-back 90-degree panels can be separated by as little as 10 inches or as much as 40 inches on either side of the master tower. That's really what an RF splitter is designed to do. Keep in mind that RF splitters may be used to keep track of power output on a wireless LAN link as well. And what this means is that by hooking a power meter to one output of the splitter, where really there's nothing else connected to it, you can actively monitor the output at any given time. That's probably a better use of a radio frequency splitter in today's wireless LANs. In this scenario, the power meter, the antenna, and the splitter have to have all equal impedance, however. It's very important. You can then have, at any time, the ability to access the line to be able to check the output power of your radio frequency line. Once again, though, this is part of a radio frequency system. So because it is yet another device that has to be tracked, keep in mind that the splitter must be certified by the FCC as part of a system if it's going to be used in your wireless LAN. When choosing an RF splitter, there are several things to think about. The insertion loss is probably the main one. How much of my signal amplitude is going to decrease when I actually put this radio frequency splitter in line? The frequency response is also something to consider. I want to make sure that the specification of the splitter is at least as high as the highest frequency